Hello, the purpose of this video is to look at some IB stock questions as it relates to a subtopic called curve sketching. One of the things that we study when we study functions is we try to identify places where the function will turn around. It's called a maximum or a minimum. It's also called a stationary point. And stationary points exist when the first derivative is equal to 0. Since the first derivative is talking about the speed or velocity or rate of change, when the rate of change is equal to 0, we can say that the function was stationary at that point. So, without further ado, let's go to IB style question. We're given a function, and we are asked to find the y-coordinate of the stationary point. And in fact, it even tells us what the y-coordinate of the stationary point is. We just have to prove that that's a correct statement. So a lot of times you see the term show that in IB. Essentially, they're giving you the answer. You just have to prove how that answer is gotten to. Just like any problem where you're asked to find stationary points, you need to find the derivative, and you need to set the derivative equal to 0, because that's, again, where the function is stationary. So you can see here, the first thing I did was I wrote the function. Now notice it's not the derivative yet, but I wrote the function in power form, so I can use the power rule and the definition of the derivative of natural log, which is 1 over x. Here we notice we multiply the coefficient 1 by negative k, so we get that, and then we drop the power by 1. To make this more algebraically appealing, I'm going to take the negative k, negative 1, and move down to the denominator, so this is actually k over x to the k plus 1 instead of negative k minus 1. We factor out the negative 1 and move everything down to the denominator. In order for this term, subtract this term to equal 0, the two terms must be equal to each other. In other words, we add k something over to both sides. And then we factor out an x. Notice again here that x to the k plus 1 is the same as x times x to the k. So I factor out that x. Notice if we redistribute, we'll be back where we started from. And now I use the zero product principle. Either x could be 0 or x could be equal to the kth root of k. Notice I wrote it as k to the 1 over k power. That's the same as the kth root, not the square root or the cube root, but whatever k is. We're going to root that. Now, I actually realized when I look at the original function that we cannot take the natural log of 0. So 0 is not in the domain, f of 0 doesn't exist, therefore it's not a stationary point. However, when I substitute in k to the 1 over k power into the function, I get the natural log of k to the 1 over k, to which I apply the power rule and bring the exponent down in front. Then we have the natural log of k. Also, if we take k to the 1 over k to the k power, today's lesson was brought to you by the letter k, we get 1 over k. Factor out the 1 over k, we're left with the natural log of k plus 1, and I'm pleased because that is the same effectively as natural log of k plus 1, all divided by k. It's the same as distributing a 1 over k into the sum k and natural log of k plus 1. So that's what's done. Now it should be worthwhile to examine this function with k's being changeable. I want to show you that here on the Desmo. Particularly, what I'm going to do is start with, well, first of all, notice that negative k values, there is no maximum. The function is just always increasing forever. So when k is negative, there is no maximum. So we're just going to talk about positive k values. Actually, first I'll look at when k equals 0. When k equals 0, then it's just the natural log function. This is y equals the natural log of x. So that's kind of cool. But then as soon as we let k get bigger, we can see that the function behaves a little differently, and we get a maximum, right, or a minimum rather, right here. What's fun to watch is what happens to the function. You can see that the location of the minimum is constantly changing as the k changes. But what the problem was teaching me was that location of the y-coordinate is totally predictable. All you have to do is take the natural log of k, add 1, divide all that by k, and that will be the minimum point on your graph every time. So I always like to think about the meaning of my results when I do math, especially in IB. Beyond just getting the answer correct, I want to think about the whole problem. So that's why I'm trying to illustrate that here. To continue, though, let's look at one other example of a problem, and this is the red letter problem, so it must be the most difficult problem in the section. And all it's saying is we've got a function y equals kx cubed, it's a cubic function, plus 6x squared, and we are supposed to find and classify the stationary points on the curve. Again, what's happening here is the curve is a family of curves, actually, where it's always going to be a cubic function, but depending on the value of k, the nature of the cubic function is going to change. And what I can see with this technology is there's going to be a fixed local minimum. This is a local minimum right here, and that's going to be the lowest point in the neighborhood all the time. That just stays put. But the maximum, the local maximum, that is to say, seems to change. It is either on the right-hand side or left-hand side, either the first or second quadrant, but nonetheless, there seems to be some predictable nature to the local maximum, and again, very predictable nature for the local minimum because it stays put. So this helps me understand the nature of the question a little better. Now all I have to do is see how the math bears out all of this that I've just witnessed. There it is. I hit the wrong button. Unpack this a little bit more slowly. First of all, I take the derivative, and in terms of k, I just treat k like any other number, like 3 or 5 or whatever. So I multiply the k times the power 3, and then I drop the power by 1, and so I get 3k times x squared plus 12x. To find a stationary point, we need the derivative to equal 0. The derivative equals 0 when 3k x squared plus 12x equals 0. This is a quadratic expression that's easily factorable. I take out a 3x. I'm left with kx plus 4. Using the zero product principle, 3x equals 0 or x equals 0. There's that stationary point I was telling you about. We put in 0 back to the original function, and we will find 0 for the y as well. So the origin is that stationary point. And here's the other stationary point. Whatever k is, my x is going to be the opposite of 4 over k. So what do we do with that information? The first thing I do is find the coordinates of the extrema, maxima and minima, or the maximum and minimum in this case. And so by substituting in 0, I get 0, that's no problem. By substituting negative 4 over k, I get the value 32 over k squared. The nice thing about this result is no matter what k is, 32 over k squared will always be positive. So given the fact that 0, 0 is a stationary point, I know that the other stationary point will always be above 0. So this is always going to be a maximum, and this will always be a minimum in the neighborhood. So just to finish up the communication piece of the written report, if you will, I state very clearly the stationary points. I found them. Now I need to classify them. So just to make sure I'm being thorough, I observe that k could be negative, in which case we would get a situation like this. K could be positive, in which case I get a situation like that. One of the things I want to do for you is just to point out that when k is negative, that means that the lead coefficient is negative, which means we're going to have negative end behavior starting from positive numbers and ending at negative numbers. Similarly, if k is positive, then we have positive lead coefficient, which means we're going to have this kind of end behavior, ending up in the positive after starting from the negative. Given the fact that 0, 0 is always stationary, and given the fact that the other stationary point is always positive, tells me that the camelback is going to be on the first quadrant in this situation, and in the second quadrant in this situation. Regardless, I know for a fact that 0, 0 is always going to be a local minimum, and I have to fix a typo here. Bear with me, please. That should read 32 over k squared. And I'll just put that in parentheses. Oops, I don't need those. Sorry, hold on. Let's keep going. I'm sorry. Hope you don't have anywhere you have to be. There we go. And I stated the same thing down here, but I realize in hindsight that it's redundant because the same truth holds or applies, and I still have that typo, so I'm not going to bother to fix that. I'm just going to cross that out, pretend it wasn't there. And then I just made a little statement here that points out that when k is negative, the value of x coordinate of our maximum is going to be a positive number, and when k is positive, we're going to have a negative location. So put all this stuff together, this equates to analysis, and that's kind of what we're supposed to be working towards. We're analyzing or using calculus to analyze things. So hope this was helpful. Have a great day.